Hey everybody, Ryan here, and welcome back to our patient management series. We're going to cover a lot of material in this video, and we're going to be talking about the evaluation of dental literature. It's really easy to get bogged down by this topic. Evidence-based dentistry can be really dry, but I'm going to hit the highlights for you. No nonsense, high-yield facts. Let's go. So medicine, and dentistry in particular, in the 1990s, underwent a paradigm shift. We used to value the opinions of experts like G.V. Black above all else. But now we value approaches based on evidence. Is there proof that certain materials and certain techniques actually work in a majority of patients? And the quality of evidence is rated from best to worst in the so-called hierarchy of evidence. At the top of the pyramid is the meta-analysis and systematic reviews. And then going from best to worst, we have the randomized clinical trials, cohort studies, case control studies, cross-sectional studies or surveys, case reports, which are reports of unique patients or findings. Then we have our expert opinions like G.V. Black. And finally, at the bottom, animal studies and test tube, lab bench, in vitro studies. And these two are not nearly as clinically relevant as the others, hence why they're italicized, because you're not using a human model. So they're at the bottom of the hierarchy. And we're going to cover a lot, or most of these, in the next couple slides. So our first big category of dental literature are the descriptive or epidemiological studies. So epidemiology is the study of the distribution and determinants of disease. And we had a whole video dedicated to this topic, so you're already experts on this. And so these studies are large-scale community-based studies to quantify the disease status in a community. How many people in this population have caries, have gum disease, etc. And so we're using these measuring tools that we talked about in the epidemiology video, like DMFT, gingival index. Think of easy measuring tools that clinicians can employ to gather lots of data on a huge entire communities, and then from that determine the prevalence of, again, tooth decay, gum disease, which is the proportion of a given population that's affected by that condition at a given time. Our next big picture group of dental literature are the analytical or observational studies. This is really the meat and potatoes of this video. And so these studies are designed to determine the etiology or cause of a disease. And note that all of these four study designs here determine association, not causation. So they may or may not represent causal relationships between a factor, a risk factor, and a condition, etc. So the first one we're going to talk about here is the cross-sectional study. And this one's very similar to what we just talked about, but on a smaller scale than the community-based epidemiologic studies. So cross-sectional studies involve a survey or measurements that are taken to represent a snapshot in time. And so this is going to measure prevalence. For example, we could examine a group of people who drink alcohol and see how many of those people have oral cancer and how many do not. So literally, you could just sample a classroom or patients at a clinic, and this all can be done in the same day. There's no need for any follow-up after you gather your data. Now, everything beyond the cross-sectional study in the slide is what's called a longitudinal study. So these three are longitudinal because it requires you to follow people over a certain period of time. Cross-sectional, like the descriptive epidemiologic studies, can be done at one point in time, just gathering whatever present data we have at that day. But these three, we have to follow patients or have to have data from patients over at least a couple years. So the case control study involves people with a condition, which are called the cases, and they're compared to people without that condition, which are called the controls, hence the name case control. Now, this is done in the past. So this is a retrospective study design, where the follow-up period I just talked about has actually already been completed. So for example, you'd have separate groups of people, and those with oral cancer and those without it, and then you'd search through their past medical records to look for the presence or absence of alcohol drinking. That's our risk factor for these examples. And you do this in order to determine the odds ratio. How likely is it that alcohol is associated with oral cancer? So this is a retrospective study because we're looking in the past, but it did involve some period where the patients had to be followed. So it's still, in this case, it's still a longitudinal study design. Next, we have the prospective cohort study. So these next two are both cohort studies. So a cohort is a group of subjects followed for a long time to see if they develop some condition. So prospective cohort study means that the cohort was followed through time to see who develops a certain disease. So let's say we track a group of people for 5 years to see how many of them develop oral cancer. And then we would compare the incidence of oral cancer in people who drink alcohol and those who do not. An incidence is the number of new cases that appear over time. And then from that information, you could determine the relative risk, which is probability of drinkers getting oral cancer versus non-drinkers getting oral cancer. And lastly, we have the retrospective cohort study, where we would look back after following this cohort and decide, well, you know what, maybe we want to see who developed caries. And so then we could compare the incidence of caries between the drinkers and the non-drinkers. So it's retrospective because patients were already followed over time and the data is already there. Now we just need to compile and analyze that data. So some people ask, well, what's the difference between retrospective cohort study and case control study? Because they're both retrospective, they're both looking in the past, and I don't really understand what's the difference between the two. So the retrospective cohort study tries to determine the risk of developing a disease with already known exposure factors. So say we already know that alcohol contributes to oral cancer, that smoking is linked to periodontal disease. Whereas the case control study will try to determine the possible exposure factors after a known disease incidence. So they're essentially flip-flops from one another. One's trying to gather information about risk of developing a disease, and we already know the exposure factors. The other one's trying to figure out what possible exposure factors there are. So it's a really important distinction to make, and hopefully that can help simplify those four seemingly complex, but when you break it down, not too bad analytical study designs. And for the board exam, I bolded prevalence, odds ratio, and then incidence and relative risk because they like to ask about that. So if you can simply remember which of the study designs are trying to gather which data, that's really helpful for the exam. And lastly, we have the experimental studies. And these ones try to determine the effectiveness of a given therapy. So think a medication or drug, etc. So the randomized clinical trial aims to isolate one factor, say a new drug, and examine its contribution to a patient's health by holding all other factors as constant as possible. And that's really hard to do. But the best tool is randomization. So you would get a probability sample where you randomly select people from a list or database and then randomly allocate those individuals into different treatment groups using a random number generator or some equivalent. And so randomization, both of the selection of the people you're using in your study and then how they're allocated into different like placebo and experimental treatment groups, randomization minimizes selection bias and is the best control for confounding variables, which we'll talk about a little bit later in the video. And blinding is another great method for creating an ideal clinical trial. Blinding means concealing allocation information to minimize the biased assessment of outcomes. So a single blind study means that the participants or the subjects are blind to what group they're in. They don't know if they're taking a placebo or they don't know if they're taking this new drug. Double-blind studies are even better because both the participants and the experimenters or the investigators are blind, and the subjects don't know what drug they're taking, and the investigators don't know what data they're collecting for which group. So that's the best way to blind a study. All right, so let's get into more of the nitty-gritty with the biostatistics. And so some of this stuff is definitely tested on the board exam, and I'm going to try to hit the highlights so we don't get too bogged down into the nitty-gritty details. So frequency distributions refer to these curves down here. We have a normal distribution in the middle, which is this classic bell-shaped curve. In the middle is the mean, median, and mode. We'll talk about the measures of central tendency in the next slide. And if you have any extra room for memorization, you can remember that within one standard deviation from the center of this curve, you have 68% of subjects. If we go 2 standard deviations away, we have 95%. If we go 3 standard deviations away, we have 99.7% of the subjects. And so we don't have to, I don't think you necessarily have to memorize these numbers again. And if you don't understand standard deviation right now, don't worry about it. We're going to be talking about it in just a little bit. We can also have a skewed distribution, which is what these two are showing. Positively skewed if the tail, so this part is the tail goes to the right. Negatively skewed if the tail goes off to the left. Bimodal distribution just means instead of 1 peak, you have 2 peaks in your data collection. All right, measures of central tendency. This I have seen tested on quite a bit. Central tendency means it allows you to characterize a data set by some central numbers. So I'm sure you've all heard of these things at some point in math class. We have mean, which is the average value of a data set. So for the mean, you would add up, let's just have this example data set. You'd add up all of these values and then divide by the number or the amount of values in the data set. So for example, the sum of all these numbers is 95, and there are 11 of them. So we would take 95, divide it by 11, and we get 8.63. And so that would be the mean for this data set. The median is the middle value. So for this one, we simply cross out the outside numbers until we get to the middle number of the data set. So we're almost there. We go 5 from either side, and 6 would be our median for this data set. Now there's an even number of values. You'd have 2 numbers at the middle, and you simply would take an average or mean of those 2 values. And lastly, the mode is the most frequent measurement in a set of data. So for these numbers, unfortunately I've crossed them all out, but you can see that 4 is the one that occurs most frequently. So 4 would be the mode of this data set. And believe it or not, these are things I would definitely know how to do on a data set for the board exam. You could get like test scores or some epidemiologic measure and have to figure out the mean, median, or mode of those numbers. But luckily, it's nice and easy once you know how to do it. And then we also have measures of dispersion. So dispersion referring to how spread out the values are from each other. So the range is the maximum value minus the minimum value. So for our same data set, we would take the max, which is 21, and subtract 2. And so the range for this data set would be 19. Variance is how spread out the individual values are from the mean. So this one's actually a bit tricky to calculate. You never would have to do this for the board exam. But what you would do is figure out the mean, which we got as 8.63. And then for each number, so each of these 11 numbers, you would subtract the mean from that number and then square the result. So this would give you the squared difference. And then you'd calculate the average of those squared differences. So don't worry about that calculation, but for this data set, if you're curious, the variance is 42.049. Standard deviation is just the square root of that, so it would be 6.48. So the larger, and the important part here is the larger that this number is, the more spread out the values are from one another. So if we had a standard deviation of 1, all of these numbers would be a lot closer. Since we're a little bit higher at 6.48, that's explaining how we have 2 and then we have all the way up to 21. There's a bit more of a spread between these numbers. So where this all becomes especially important is considering outliers. So this is a histogram, which is used to represent variance. And in this case, it's a representation of that bell curve that we looked at with a bit of a positively skewed bell curve. And it's essentially in vertical bar format, which is how histograms are made. And you'll notice that these values follow a somewhat normal distribution, but we have one outlier way over here. And so think for a second, is an outlier like this going to have more impact on central tendency or the measures of dispersion? So will this outlier have a greater impact on central tendency or dispersion? So it's going to affect dispersion a lot more. So range, variance, and standard deviation are all way more impacted by this value, which is going to increase all of those values significantly. It's going to have almost no effect on mode or median, and maybe some nominal effect on the mean, but not a whole lot because there are a bunch of other data points here. But you can imagine that the range, whatever these numbers aren't listed, but whatever this subtracted by this, it's going to be a lot different than this number subtracted from this number. All right, now we can talk about quality of a diagnostic test. So we have reliability and validity. So reliability is all about, are you getting consistent results from that test? You have multiple operators using this diagnostic tool, multiple studies that have looked at it. How much do they all agree with each other? And I love this analogy right here. It's like shooting arrows at a target. And reliability means that your methods are reliably producing precise results that are all close to one another. So it doesn't necessarily mean like they're accurate, they're close to the bullseye, but all these arrows are grouped together quite nicely. So that's an example of reliability. Whereas validity is looking at, are they accurate results? How close to the truth or to the bullseye are those results? So say for a new diagnostic tool like Diagnostic, it came out a few years ago, which produces fluorescence for cavity detection, how accurate is it to distinguish between actual caries and no caries? Now, of course, we'd ideally want a test that is both reliable or precise and valid or accurate. So we'd want a close grouping of arrows right around the bullseye. Other things to consider are sensitivity and specificity. Sensitivity means that you're correctly, or the test is correctly identifying people who have disease. Specificity means that the diagnostic test is correctly identifying people who do not have the disease or are healthy. So how I remember this is that the S and the E are next to each other in both sensitivity and disease. Twice, in fact. So that's a great way to remember between sensitivity and specificity, which otherwise sound very similar. So this table down here is incredibly important to understand. So let's take a moment to go through what all these acronyms mean. The top row is what they actually have as determined by some gold standard measurement. So let's say, for hypothetical purposes, this is a crystal ball that tells us the absolute truth for a subject, for a patient, if they have caries or if they don't have caries. The left column is what our experimental method says they have. So say we're looking at Diagnostic. How valid, how reliable is it? And we're going to look at the sensitivity and specificity of this new experimental method. So first we have TP. This is true positive. So this means that the patient actually has caries and our diagnostic tool or test says they have caries. So this is a success. It was correct in diagnosing. Down here, FN stands for false negative. So our test says they don't have caries when they actually do. So we're erroneously excluding them from the caries group. So false negative would be a failure of the test. Now let's move over to this column. TN stands for true negative. So this means that the patient doesn't have caries and our diagnostic tool successfully diagnosed them as not having caries. So that's another means of success. And lastly, we have FP, which you can guess is false positive. And this is where our test says they have caries when they actually don't. So we erroneously assign them to the caries group. So again, our test succeeds when we have TP or TN, and it fails when we have FN or FP. So a high amount of true positive relative to false negative is when we have high sensitivity. And a high amount of true negative relative to false positive is when we have high specificity. And so a perfect sensitivity and specificity would be 1.0 for each of them. That would be having a perfect only true positive and only true negatives, and we didn't get any false negatives or false positives at all. But if let's say we got 0.5 for each of these, that's about as low as we could get, because then essentially we're just flipping a coin to see if they have caries or not. So again, if we're looking at this column, we're in the caries column. So this is sensitivity. And then this column, no caries, we're looking for the accuracy of detecting health. And so this is a great tool if you can just remember how to draw out this chart and write in these acronyms. It'll be really valuable for test day if you get any kinds of questions about sensitivity and specificity, which I guarantee will come up to some degree. All right, next let's go into inferential statistics. So statistical significance is represented by the p-value, which I'm sure you've seen in most every journal article you've read. And it's a probability that two variables are unrelated. And we usually set this p-value, as 0.05. And if p is less than 0.05, then we reject the null hypothesis, which I'll explain in the next slide. And say there's some connection between two variables. Again, let's go back to our previous example, alcohol and oral cancer. So if we're less than 0.05, we would accept that there's some connection between the two. But if p is greater than 0.05, we accept the null hypothesis, and any interesting connection between alcohol and oral cancer is just coincidental and due to chance. So the null hypothesis is a hypothesis which the researcher tries to disprove, reject, or nullify. Now, an example null hypothesis is there is no difference between caries prevalence in a fluoridated population and non-fluoridated population. And people have conducted research to disprove this exact statement, and in doing so, prove that fluoride helps prevent caries. So let's return to our table from before, because good news, it applies here too. The same as before, our top row is our crystal ball. So the first column means that our null hypothesis is actually false. So fluoride actually helps prevent caries. And the second column is if our null hypothesis turns out to be true. So it turns out fluoride doesn't help at all. And the left side of our table is once again our research results, what our data shows. So does Diagnostic work to find caries? Does fluoride work to prevent caries, etc.? So let's start with the first column, where the null hypothesis is false. So after running our statistics, our p-value is less than 0.05. So our research tells us we have to reject the null hypothesis. So our research worked. Now let's say our p-value was greater than 0.05, and we would have to accept the null hypothesis. And for this first column, this would be incorrect. So this is known as type 2 or beta error, where we accepted a null hypothesis that should have been rejected. And it's because our study didn't have enough power. Now let's look at the second column. Say the null hypothesis is true, and that's what our study said. It said to accept the null hypothesis. And so that would be a correct research result. Not necessarily a fulfilling one, but it would be correct nonetheless. But if our research told us to reject the null hypothesis when it was actually true, that is known as type 1 or alpha error. We rejected a null hypothesis that should have been accepted. That's because our p-value was at fault. All right, next let's talk about correlation analysis. So correlation, the correlation coefficient, or R, is a statistical measure that represents the strength of the relationship between two quantitative variables. And we'll talk more about quantitative versus qualitative a bit later. So this R value is always between -1 and +1. You can't have anything like +2 or positive anything above 1, anything below -1. +1 means that all the values lie perfectly on a positively sloping line. It's very unlikely that you get all the results on a perfect, that you could graph them on a perfect line, but that's the one end of the spectrum. The other end of the spectrum, -1, means that they lie on a perfectly negative sloping line. Now, it doesn't matter what the exact slope is, just how close the points are to that line of best fit. Now, as you get closer to 0, we go from 1 to 0.7. They're a little bit more spread out. 0.3, they're really all over the place, but they still kind of match this line of best fit with a positive slope. And if you get to 0, the middle between -1 and +1, that means there's no linear relationship whatsoever. So as you get closer to 0, the data points get more spread out from the line. When you get to 0, that means there's no linear relationship between the data coordinates. Now you can also do a multiple regression, and the plot looks similar to these, and a multiple regression provides a mathematical model for predicting relationships between a dependent variable and one or more independent variables. So it's a more complex version of this, but don't worry too much about that. So more inferential statistics. These are all statistical analyses that are used for testing a hypothesis. The chi-square test, and this is the Greek letter chi, measures the association between two categorical values. So let's say we ask a group of people, what do you prefer, cats or dogs? And let's say the group consists of both men and women. So the chi-square test could tell you if gender and preference for cats or dogs are related to one another. So we would make a 2x2 table, men and women on the left, and cats and dogs on the top, and then we would run a chi-squared test. And this will, again, like most tests, give you a p-value. And so this is where things kind of work itself out, and there's a lot of overlap between these concepts. Because if our p-value here is less than 0.05, we would reject the null hypothesis, and there'd be a statistically significant difference between gender and preference for cats or dogs. If p is greater than 0.05, we would accept the null hypothesis, and we could say that gender is not significant in determining preference for cats or dogs. So chi-squared comes down to comparing two groups and see how similar or different they are. The t-test is another really popular one, and this is used to compare whether the means of two groups are statistically different. So say we have a placebo group and an experimental drug group. The null hypothesis is that there's no difference between them. And we're hoping there is a difference, and it would mean that the new drug is efficacious. So t-test will help us prove if there is a statistically significant difference, if p is less than 0.05, or if the difference, if any, is just due to chance, p is greater than 0.05. So hopefully you can appreciate that, again, a lot of these concepts overlap and flow into one another, which is great for us because it's less we have to memorize. The z-test serves the same purpose as the t-test, but it's used if there's a larger sample size, so n is greater than 30 is kind of a rough ballpark to use, and if the standard deviation and variance are known. So the z-test is a little bit better. There are a couple other things between these two, but for the board exam, this is plenty to know. And lastly, we have ANOVA, Analysis of Variance. That's what it stands for. And this is basically a t-test, but between two or more means. All right, operational variables. So these are important to define and know what they mean. And again, lucky for us, it's really not too complicated once we boil all of this down. So qualitative means descriptive. These are qualities. If we talk about nominal qualitative variables, nominal means they're based on names or labels. So we could have binary variables like yes or no, right or left, or ternary variables which have three different options. And examples of nominal variables used in dental literature could be genotype, blood type, hair color, eye color, etc. And so these are things that you'd use or see in like a chi-square test, these qualitative descriptive variables. Ordinal variables involve a ranking of some sort. So examples of ordinal variables would include like socioeconomic status, where you have low, middle, or high income, education level, where you could have high school, bachelor's, DDS, DMD, or something, let's say, orthodontics related, like mild, moderate, or severe crowding. So there's a clear ranking involved with the variables being used. Now I put an asterisk here because ordinal can also be quantitative. So quantitative variables are numbers, they're quantities. So an example of an ordinal quantitative variable are things like the Likert scale, which is you would ask on a survey in a cross-sectional study, rank this on a scale from 1 to 7, with 1 being not at all likely and 7 being extremely likely. Or a net promoter score, which you can see sometimes on surveys following the use of some kind of product. And so a net promoter score would rank from 0 to 10, how likely you are to tell someone about this product. So these are rankings, but they're represented by numbers. So, and that can be really useful for statistics to have a clear quantitative values that you're gathering. Interval variables are a range of values. So examples of interval variables include temperature, pH scale, SAT scores, etc. And lastly, we have ratio variables, which involve a range of values again, but with a clear definition of 0. So examples of ratio variables include reaction rate, pulse, weight, length, temperature in Kelvin, where we have an absolute 0, basically an interval variable, but with a clear 0 point. So for qualitative variables, we're using the chi-square test. For quantitative variables, we would be using a t-test, z-test, ANOVA, etc. Some more definitions to know. Independent variable, I've already thrown this around a little bit. This is like our x if we have an xy plot. And so the conditions or factors of an experiment that are manipulated or controlled by the investigator. So this would be like the type of treatment being compared, the placebo and the experimental drug, things like that. Whereas a dependent variable, or the y-axis, is the measure or outcome thought to change as a result of the presence, absence, or manipulation of the independent variable. So this would be like mortality, disease outcome, health status, cost, etc. And lastly, we have the confounding variables, or covariates. So these, I mentioned before, can adversely affect the relationship between these two. It muddies the waters, so to speak, between x and y. And this can cause the researcher to analyze the results incorrectly. The results may show a false correlation between x and y, lead to an incorrect rejection of the null hypothesis, etc. So it cause a lot of different issues. And confounders could be gender, age, ethnicity, anything that maybe wasn't controlled for in the experiment. So what do we do about this? Well, we can minimize confounding variables by randomizing. Because if we have large sample sizes with randomly sampled and allocated groups, hopefully all of the confounding variables will be randomly and uniformly distributed among those different groups. So randomization is our best friend. And lastly, we have the components of a scientific paper. The PubMed is a common database used by medical and dental students and medical and dental professionals that contains a whole host of electronic dental literature. So the board examiners like you to know the framework, the basic framework of a dental paper or any scientific paper for that matter. So the title is simply that, the title of the study, which should indicate some central question or focus of that particular journal article. The abstract is essentially the SparkNotes version. It appears at the beginning of the paper and provides a quick summary of the background, the population being tested, findings, and main conclusions. The introduction section provides a background on the topic, why it's important, why it's relevant, a literature review of what's currently available on the topic, and then clearly states the purpose and aims of the study, and a hypothesis for the study. So your null hypothesis, what you're trying to disprove, and ultimately what you're trying to prove with your research. The methods section provides specific information about the population being tested, the independent and dependent variables, the sampling method, the experimental design, the statistical analyses performed, everything we've essentially covered in this video. And a good litmus test is that the methods section has enough information that anyone would be able to replicate that study if they had the proper resources. So the methods section allows the reader to assess the validity and the reliability, right, the quality of the diagnostic tests being used. And I think it's often overlooked. This is probably arguably one of the most important sections of the paper. And unfortunately, if someone's short on time, this is typically the section that people will skim through. But again, the methods section tells you a lot of information about the paper and the research that was conducted. The results section describes specific findings and outcomes from the study. The discussion section interprets and makes sense of those findings. And the conclusion provides a summary and attempts to draw connections between the findings and the original question and hypothesis that they introduced in the introduction section, or at least the paper should do that. And finally, the references at the end is a list of papers the authors used, so people could go find additional resources if they wanted to learn more about a certain aspect of the topic. All right, so that's it for this video. Thank you so much for watching. I know it's a lot of information, but this is some really high yield stuff to know for the board exam, so definitely rewatch the video if you need to, because I definitely covered a lot on evidence-based dentistry, biostatistics, and a lot of other things. So thank you so much for watching. I hope you enjoyed it. If you're interested in supporting the channel, please check out my Patreon page. A huge thank you to Michael Raja, Reb Boyd, Leonella Bunger, David Jaden, Yanet, Nicole, Isabella Caldis, and all of my patrons for their support. You can unlock extras like access to my video slides to take notes on, and practice questions. So go check that out. The link is in the description. Thanks again for watching, everyone. I'll see you in the next video.